We present a machine learning technique for turning any camera into a depth camera for interactive scenarios. In this example, we demonstrate our depth sensing technique on a modified mobile phone camera, allowing for 3D skeletal tracking of the hand. Our technique is designed specifically for close-range interactive scenarios where we want to sense hands or faces of the user. Our technique works as follows. We use low-cost, low-power LEDs to illuminate the scene. We remove the IR cut filter on the camera and replace this with an IR bandpass filter. We then learn a mapping from this IR intensity image to depth using a hybrid classification-regression forest. Here we demonstrate that any web camera, such as the Microsoft LifeCam, can easily be turned into a depth sensor in less than 10 minutes. We first remove the infrared cutoff filter from the lens. We then add a ring of infrared LEDs that is attached to the camera with a 3D printed case. Finally, an infrared bandpass filter is attached in order to block most of the ambient illumination. The modified web camera now only captures the infrared illumination, here visualized in red, which we use for our depth estimation algorithm. Learning a mapping from IR intensity image to depth is performed in a two-layered process. We first perform a coarse discrete depth classification, followed by a fine continuous depth regression. Whilst clearly not a general-purpose depth camera, our system can be used in a variety of human-computer interaction scenarios. Our system produces accurate results in real time with up to 220 frames per second depth estimation. State-of-the-art pose estimation techniques can be employed for hand part labeling using the inferred depth data to enable 3D interactions. Here we compare the results of our depth estimation technique, shown bottom left, with the Xbox One time-of-flight camera, shown top left, and a more naive depth estimation technique based on the inverse square law, shown top right. Our system works equally well for faces. Here we show the error between our technique and the time-of-flight technique from Xbox One. Our use of a narrow bandpass filter and the ability of subtracting a background frame with ambient illumination allows some level of robustness to ambient IR. Given the accuracy of our depth estimation algorithm, we can plug into existing components that work from depth maps. For example, here we can apply facial part classification and expression detection for controlling an avatar. Here we highlight the quality of the depth estimation technique by fusing multiple depth maps into a single model using the Connect Fusion system. Note that in this case, the system has been specifically trained for the person in question. In this example, we demonstrate how our learning technique can be applied to untrained faces, as well as untrained hands. In this final example, we demonstrate the main limitation of our system. Because we train for a specific surface albedo, in this case skin, surfaces with other reflectance properties will cause errors in the depth estimation algorithm. However, for interactive scenarios focusing on faces and hands, our method provides a low-cost and efficient way for turning any camera into a depth camera.